Okay guys, let's take a moment and copy down the problem as well as the equation. All right, I know you're rolling your eyes about solution stoichiometry, but it's really not as difficult as the gas stoichiometry that we did last chapter. The reason for this is we are going to use the molarity as moles per liter, and we literally take the molarity and make it a conversion factor in our dimensional analysis. With the gas law stoichiometry, we had to incorporate the gas laws, and we had to know which gas law we were using and a combination of them, and that was pretty complicated. Solution stoichiometry is not that difficult. So a couple of things to keep in mind here as we move through the problem. Remember, molarity is equal to moles over liters. So what that means for us then is that if we have a 0.25 molar solution, we have 0.25 moles of sodium sulfate over 1 liter of sodium sulfate. We also can write the same thing for our barium nitrate. So instead of writing 0.15 molar, we're going to use 0.15 moles of barium nitrate per 1 liter. If you look at the fraction, these are conversion factors. We may have to flip them, but they're usable for us in dimensional analysis. So sorry guys. Let me shrink that down and get this out of here. All right. So we have our molarities. We now know our molarities will be used as conversion factors. So the only number we really have to start with is 12.5 milliliters. All right, so 12.5 milliliters. We can't do anything with milliliters. So I'm sure you've already guessed we're going to convert to liters. So 1,000 milliliters is equal to 1 liter. Now, this is all for our barium nitrate solution. So now we're going to convert our liters to moles because we know the molarity. So we get rid of liters, and we know that for every liter of our 0.15 molar barium nitrate solution, we have 0.15 moles. Okay. So we can get rid of our liters that way. Now we can use the mole ratio from the equation. If you take a look at the equation, we have 1 mole of barium nitrate for every mole of sodium sulfate that's used. So this is a 1-to-1 ratio. We write 1 mole of the barium nitrate to 1 mole of the sodium sulfate. Shrink that down. Uh-oh, that guy didn't go. Okay. Okay, now we got out of moles of barium nitrate 2 moles of sodium sulfate. So now we have to get rid of moles of sodium sulfate and get to milliliters because we want to know what the volume is in milliliters. So we use the molarity of this. We know that we have for every 0.25 moles of the sodium sulfate, we have a liter of solution. And we learned that based on our molarity. Uh-oh. Sorry, guys. I got to put in Na2SO4. Okay, but we're not asked for liters, we're asked for milliliters. So our last conversion is to get rid of liters. 1 liter to 1,000 milliliters. Let me shrink that guy and put him in. When we do all of the math, we literally type in 12.5 divided by 1,000 times 1.5. We skip over to divide by 0.25 times 1,000, and we get, on our calculator, we round to 7.5 milliliters. 7.5 milliliters of 0.25 molar sodium sulfate. And that is our answer. And that, guys, is how you use solution stoichiometry to solve various problems. Okay, please take a moment and write down the problem. All right, I'm sure you're anticipating how can the problems get harder. Here's how they get harder. They don't give you the equation. At this point in the year, you are capable of writing and balancing your own equation. So in this problem, they have you do it. They tell us that calcium oxalate is very insoluble in water, aka it precipitates out. What mass of sodium oxalate is required to precipitate the calcium ion from 37.5 milliliters of 0.104 molar calcium chloride solution? All right, guys, so some key things here. They give us the formulas because they don't expect us to know that. That's very nice of them. You will not have that ability on the final. You will need to know your own formulas. But let's take a look at what happens. We know that we're going to have the sodium oxalate react. So we have Na2C2O4, and this is aqueous. Since they're talking about precipitation, they're talking about a precipitation reaction, which we learned about in our different types of chemical reactions. Now, what's happening here is the calcium is getting precipitated from the calcium chloride, so that is our other reactant. And since this is a double displacement reaction, if you recall, your outer ions hook up, so we're going to make some salt water, and then our inner ions hook up and we make the calcium oxalate, which is the insoluble product. So let's write those down. Let me shrink this part down just a hair, maybe. Okay. So we're going to make sodium chloride, which we know is aqueous, and the calcium oxalate, which is a solid, because they tell us that it's very insoluble in water. That means it's a solid. Now to balance, we need a 2 in front of the sodium chloride, and then we're done. Let's shrink that all down. Okay, just like in the last problem, now it becomes a how do we use dimensional analysis to solve the problem, and what do we do with molarity? So if we know we have a 0.104 molar solution, then we know that we have 0.104 moles of calcium chloride for every 1 liter. So we'll end up using this most likely for some sort of a conversion here coming up, okay? So what's our given? 37.5 milliliters, that's correct. So we have 37.5 milliliters, and that's of the 0.104 molar calcium chloride. But in order for us to use that molarity as a conversion factor, we have to get to liters. So we're going to take our 1,000 milliliters for every 1 liter. Now we can use the molarity of the solution. For every 1 liter, we are told that we have 1.104 moles of calcium chloride. Now that we've got moles of calcium chloride, we can convert to moles of sodium oxalate, which is the problem that we're looking at. We're asked again, what mass of sodium oxalate is required? So we're going to now use the chemical equation that we wrote in order to convert from moles of calcium chloride. If you look, we're going to build our mole ratio. It's a 1-to-1. So 1 mole of calcium chloride to 1 mole of sodium oxalate. The last step for us is to now convert the moles of sodium oxalate to grams of sodium oxalate using the molar mass. So we're going to get rid of our moles of sodium oxalate. And using the periodic table, our molar mass of sodium oxalate is 134 grams. When we put the math all together, and we do all of our multiplying and dividing, we find that in order to precipitate 37.5 milliliters of 0.104 molar calcium chloride, we need 0.523 grams of sodium oxalate. That's it, guys. This is how we incorporate stoichiometry into our solution work. We take our molarity and we make it a conversion factor in our dimensional analysis. Have a wonderful evening.